Hello everyone, today we are going to review parametric distribution. You can find most of the contents in the Coaching Actuary ASTAM prerequisite section, where in the section 2.2 are mostly about this parametric distribution. So the definition of a parametric distribution can be defined as follows. A parametric distribution is a set of distribution functions. Each member within the set is determined by specifying one or more values called parameters. Examples of commonly used parametric distributions are exponential, Pareto, normal, and Poisson. An alternative to a parametric distribution is the empirical distribution, as we discussed in Note 1. So the empirical distribution really just means we don't know the real distribution of the random variable. So we just have a sample of it. We record the sample and we use this sample to determine or to approximate the real distribution, which we don't know. But opposed to this, or in contrast to this empirical distribution, is the parametric distribution, where you know exactly how the random variable is distributed, and it can be defined by these parameters. That's why it's called parametric distribution. Okay, let's talk about the first distribution that we are going to review, Pareto distribution. If x follow a Pareto distribution with parameter alpha and theta, then x has the following PDF: fx is equal alpha times theta to the power of alpha over x plus theta to the raised to the power of alpha plus 1. And from the SOA spreadsheet, they also provide a formula for this for you to use during the exam. But of course, it's best that you are very familiar with this and don't need to refer to the spreadsheets all the time. A Pareto distribution is recognizable from its PDF denominator having the term x plus a constant, here in this case x plus theta, and raised to a positive power, and its numerator being a constant alpha times theta alpha. Or you can also just use C to denote that. Note that a Pareto distribution only has k moment where k is less than alpha. For example, when alpha is less than or equal to 2, the second moment does not exist. And neither does the variance, because the variance depends on the second moment. And actually we can see it from here. Variable x is equal theta over alpha minus 1 squared times alpha over alpha minus 2. So if alpha is equal 1 or alpha is equal 2, you can see the variance, the denominator will be 0. That's why it can have, if alpha is equal 1 or 2, you cannot have a variance, because this will be 0 in the denominator. Then variance of x is infinity. But generally, why do they say the attribution only has a k moment where k is less than alpha? This is can be explained like this. So E maybe and k. Okay, let me do it here. E is xk times c x plus theta alpha plus 1 dx. If your k is greater than or equal to alpha, basically this is alpha. This x alpha will be cancel out with least alpha. Basically, you have something like this, and since it's from 0 to infinity, then this whole thing will be infinity. That's why it doesn't exist. Of course, this is just very simple for alpha. If k is more than alpha, higher than alpha, then this will be even higher. Then this will be only get higher. That's why it's still infinity. So that's why k has to be less than alpha if you want to have the k moment. There's a special property of a Pareto distribution that we should know. So if x follows Pareto distribution alpha and theta, and if y is equal x minus d, and x is greater than d, then y is follow the Pareto distribution alpha and theta plus d. So in this case, when x follow Pareto distribution alpha theta, y is follow Pareto distribution alpha, but theta becomes theta plus d. Why is that? We can prove this using the definition of this Pareto distribution and the definition of this. So in the box to the right, we can see the cumulative distribution. Fyy is equal probability of y bigger y less than small y. And further, we can replace y with x minus d, and condition on x greater than d. Then further, we can reorganize this to become x less than or equal to y plus d, condition on x over d. And here, since we change it to x as the random variable, we can use the survival function here for it. So basically, it's a survival function x minus survival sx y plus d over x d. Then further, we can organize it into this by dividing the terms, both terms by x d. And then we can utilize the Pareto distribution's fx function and replace it for both this and this, and further it can be organized into this. This is really just a Pareto distribution function that where theta is becomes theta plus d. That's why this special property of a Pareto distribution can be proved when x is equal, when x follows Pareto distribution alpha theta, y is equal x minus d, and the condition on x greater than d, then y will follow the Pareto distribution, but with a parameter alpha and theta plus d. Okay, there's also a reading assignment in example S.2.3.1 in the coaching actuary FA. So you have to go to the ASTM prerequisite. TAM. Then you go to course prerequisite. Then there is a section S2.2. You can find it there. Next concept that we are going to talk about is scale distribution. A parametric distribution is a scale distribution if when a random variable from that set of distribution is multiplied by a positive constant, the resulting random variable is also in the same set of distribution. For a random variable with non-negative support, a scale parameter is a parameter for a scale distribution that meets two conditions. When a member of the scale distribution is multiplied by a positive constant, the scale parameter is multiplied by the same constant. And when a member of the scale distribution is multiplied by a positive constant, all other parameters are unchanged. So in this case, two conditions. For the scale parameters, it will be multiplied by the same constant when the random variable distribution is multiplied by the positive constant. But for all the other parameters, it should remain unchanged. Let's look at this example to further understand the scale distribution. So if X follows Pareto distribution, alpha and theta, and Y is equal to C times X, where C is a positive constant, then again we can start from the CDF Fy, Y, which has a probability capital Y less than or equal to small y, which we can replace y by Cx, and further we can transform it into the distribution of x, so it becomes probability for x less than or equal to y over c. Then since we know the distribution for x is follow Pareto distribution, then we can write it out as this. And further it can be organized into this. So compare this to the regular Pareto distribution, we can see that here the theta, the new theta is really becomes C times theta. That's why in this case, the theta is the scale parameter. It's scale by C, but alpha remain unchanged. Alpha is still alpha. That's why we say that y follows y is a scale Pareto distribution. Well, the parameter is alpha and c theta. So in this case, we prove that Pareto distribution is a scale distribution. Further, if we want to apply this concept into a real-life example, here is the example. Claim size X expressed in dollars follows a two-parameter Pareto distribution with parameters alpha is equal to 5 and theta equal to 90. A euro is worth $1.2. Calculate the probability that a claim Y will be for 100 euros or less. So Y is X is dollar, Y is euro. So when we convert X to Y, we divided dollar amount by 1.2 to get a euro amount. That's why Y is equal X over 1.2. So starting from the CDF, we can get the probability of Y is less than or equal to 100 euros is the same as X divided by probability for X divided by 1.2 less than 100 euros. This can be further transformed to Px less than 120. Then in this case, we know alpha and theta, we know X follows Pareto distribution, then we can calculate the Fx using the formula is this, and we got the final result this. But alternatively, if we know from the beginning that Pareto distribution is a scale distribution, in this case, the scale constant C is actually 1 over 1.2. C is equal 1 over 1.2. So in this case, we just need to replace the new theta to calculate y, possibility of y less than 100. So theta new will be just be this 90 times c, which is 90 divided by 1.2, 75. Then we know y follow the Pareto distribution with constant with alpha and c theta, where c is the constant 1 over 1.2, and we further deduce theta is equal to 75. Then we can just directly apply the formula and calculate this possibility of y less than 100, which you will get the same result, 0.9855. Here is another example of scaling random variables. If claim size x initially follow a probability distribution with a CDF fx is equal to 1 minus square root of x over 1 plus x is greater than 0, claim sizes are inflated 20% uniformly. Calculate the probability that claim will be 460 or less after inflation. So starting from CDF y for y, our probability of y is less than 60. Then further we replace y with x. So y is equal to 1.2x. Then further we transform it into the probability with regard x. So p is less than 50. From here we can use the CDF fx function that was given to calculate the probability, which turned out to be this. So in this example, we don't know whether this is a scaling distribution, but we just did the scale of the random variable, which if we know the fx, we can still deduce the probability for y. So if we recall what we did in the past few slides, when we do the scale distribution, we are really doing a transformation process where we first determine the CDF of x, then we restate the CDF of y using the CDF of x, then determine the PDF of x, y. So this is the general process when you are given a distribution of x, but you are also asking for the distribution of y, where y is some kind of function of x, then we can always follow this kind of step to get to the final result. Here is another example where fx is given as this 1 over 5 e to the next 5 divided by 5 power. Then, but you are given a random variable y, where y is the inverse of x. Then we always follow these three steps. First, we determine the CDF of x. We know it's this, and we can integrate it, and we can get the result to be this. Then the second step is that you restate the CDF of y using the CDF of x. So eventually we get here. Then from here we can use the definition of PDF, which is the derivative of CDF. Then we can calculate the PDF of y here. So this is a generalized process for you. Whenever you are encountering a question where it requires transformation, or talking about distribution of x, then giving you distribution of y with regard to x, then you can always find out the distribution of y. The next distribution that I'm going to review with you guys is the normal distribution. I'm sure you guys are pretty familiar with normal distribution because this it has been used in many areas. So if x follow a normal distribution with mean, mu, and variance omega squared, then x has the following PDF. Fx equal 1 over omega times square root of 2 pi and multiplied by e to the power of this, where x is from negative infinity to positive infinity. And there are some more formulas here. This formula will be given in the exam spreadsheet. And we know generally the normal distribution is like a bell shape. You can see from the shapes on the right. And when the variance is 1 and the mean is 0, we noted as z, where z follows the normal distribution 0 and 1. After learning the normal distribution, naturally we are going to talk about log normal distribution. Why do we have a log normal distribution? This is because in real life, the variable is not always from negative infinity to positive infinity. Some of the random variables just start from 0. That's why with the log normal distribution, you can easily convert the normal distribution to log normal distribution when the random variable only has the x greater than 0 support. Now, from the normal distribution f(x) is equal to this, we can derive for log normal distribution f(x) would be this. You can see the difference is where x will be replaced by log x here, but also you will have x here. This x here is basically the derivative of natural log x, which is x 1 over x. So that's where this x comes from. Okay, because if you do this, you have x, and this is using the chain rule. If you have f(g(x), derivative would be f(g(x) times gx derivative, where gx here is log x. Derivative of gx would be 1 over x. You should all be familiar with this ex and the variable of x. Here is an example of scaling a log normal distribution. If x is log normal with parameter mu and omega, then cx is log normal with parameters mu plus natural log of c and omega. This can be derived as follows. This is the same step that we mentioned earlier in the transform slides, where you start with y and you convert it into x, then you utilize the x distribution to derive the probability. So here, after transformation, we can get this, but then we can utilize the definition of the normal distribution log normal distribution to further derive it until you finally get to here, where it proves that mu becomes mu plus log c, natural log c. Here is an example of applying this scaling process to the real-life example. If claim size in 2016 follow a log normal distribution with parameter mu is equal 4 and omega equal 2, claim size grows at 5% uniform inflation during 2017 and 2018. Determine a variable probability density function at 1000, F1000. So here it's a similar process, but since we already knew the result, then we just apply the concept from previous slides to here, where you have a new u which is equal old u mu plus log c, where c is 1.05 in this case. Once you get the mu and omega, then you can just apply it to find the probability of F1000, which is 0.000075. Now let's review some other common parametric distributions. First one is the most simplest one. It's uniform distribution on the interval a and b. So it means the random variable will fall between a and b evenly. So which has a constant density fx is 1 over b minus a. Then further, the fx is x minus a over b minus a. Which can be derived from this integral of ft over t. And the variance of x will be b minus a squared times 12. The next distribution that we are going to talk about is beta distribution. Beta distribution has three parameters a, b, and theta. It has the following PDF, and the support is 0 less than x less than theta. A beta distribution PDF is recognizable from the finite support. Finite support means support is from 0 to theta, and it's purely polynomial terms. That is no negative power for x. Here, purely polynomial terms here, and no exponential or logarithm terms. Here is the expected value of beta distribution and variable. On the spreadsheet that was given by SOA, there will also be EX squared, the second moment. Now, let's look at this example quickly. Fx is equal Fx 105 times x to the fourth power times 1 minus x squared. So from here we can see first x is from 0 to 1, and it has finite support 0 to 1, and the fx function is all polynomial terms. So I think we can decide that this is a beta function. Now the next step is determine these parameters. So since 0 less than x less than 1, which gives us theta is equal 1. Theta is equal 1. Then here is x to the fourth power, but here is alpha over x. So basically R and b minus 1 is 2. So b is 3. Here x alpha, but there's a divided by x here, so it means alpha or a minus 1 is equal 4. So this gives you a is equal 5. So basically this is a beta distribution with these parameters. Once we have this, we can calculate second moment of x using the formula. The formula of second moment is this. Here, theta squared a plus. So this is the formula for ex squared. You can also find it in the spreadsheets. The formula sheets from SOA you may not find it now because it might disappear, but you can find it in my course. I add a section called SOA, and in that section I post the formula ASTM formula sheet there. I will also post other things that I think are useful and related to exams there. So the next distribution that we are going to cover is gamma distribution. Gamma distribution have two parameters, alpha and theta, and X has following PDFs. X of X is equal to this. The gamma function is interpreted as gamma n is equal n minus 1 factorial. So it means it's n is equal n minus 1 times n minus 2 times n minus 3 until it reaches 1. I hope at least you guys should understand this. And a gamma distribution is commonly recognizable from its PDF of the term e raised to a negative multiple of x multiplied by x raised to a positive power. Let's talk about this part. And fx can be simplified by this. Ex of gamma distribution is just alpha times theta, and variance of gamma distribution is just alpha times theta squared. The next distribution that I'm going to talk about is the exponential distribution. Exponential distribution is a special case of the gamma distribution. It's a gamma distribution with alpha is equal to 1. You can see the PDF is simplified to this when you set alpha is equal to 1 from previous slide. And another special property of this exponential distribution is that it has the memories property, which just implies that what happened in the past does not affect what will happen in the future. For example, assume the time until the next event is exponentially distributed with mean theta. It means that regardless of how much time elapsed before the next event, the average wait time is still another theta minutes. From a mathematical perspective, the memories property means for x minus d, x greater than d will follow the same distribution of x, where d is a positive constant. So based on this, if x minus d condition on x greater than d still follows the exponential distribution theta, then the expected value of this would still be the same as this. Similarly, expected value of x minus d condition on x greater than d will be the same as x, and so variable will be the same, variance will be the same. Similarly, this would be the probability when x is greater than d is less than a. So exponential distribution, we can think a situation like when you have a event where people comes in a time that you don't know whether it's how long it is, but whoever comes in first doesn't define whoever comes in later. So it doesn't matter who comes first, but the second people, the waiting time for the second people will always start from fresh. It's like you still don't, the first people doesn't determine how long will the second people will come. That's why it's called memories property. The Weibull distribution is a transform exponential distribution. So for y, follow the exponential distribution with parameter mu, and x is equal 1 y to the raised to the power of 1 over tau. Then x follow the Weibull distribution. Theta is equal mu raised to the power 1 over tau and tau. So it has the PDF as follows. So when tau is equal 1, the Weibull distribution is actually exponential distribution. The Weibull PDF is similar to gamma PDF except the x over theta in exponential is raised to a positive power. Use this fact to differentiate between Weibull PDF and the gamma PDF. So this raised to a positive power. This is the Weibull PDF. The last distribution that I'm going to talk about is single parameter Pareto. To learn this single parameter Pareto, the easiest way is to compare it to the regular Pareto. So I put the regular Pareto in the circle, in the red circle. So compare these two, we can see that the fx is slightly different. For regular Pareto, fx has a denominator of x plus theta, but for single parameter Pareto, the denominator is just x raised to the power of alpha plus 1. So that tells us that a single parameter Pareto is just a Pareto distribution shifted by theta. So if you let y follow the Pareto alpha and theta, and x equal y plus theta, then x will follow the single parameter Pareto.